So this lesson is to help understand one of two special triangles, the first being a 45, 90 degree triangle. And what we mean by a 45, 90 triangle is if I take a look at this triangle, which was created by cutting a square in half. And if you think about the corners of the square are 90 degrees, so when you take a square and cut it in half, this corner is a right angle, 90 degrees. And then this angle, because I cut a 90-degree angle in half, then right in here would have to be half of 90 or 45 degrees. And same with this corner here is 45 degrees. And so really literally any of these squares that or triangles that I've drawn on this paper are half of squares. And so anytime you take a square and cut it in half, you create a 45, 45, 90 triangle. The angle measures in these sides. Now one of the things that happens with a 45, 45, 90 triangle is the side lengths here, 1 and 1 are the side lengths. The hypotenuse, the long side here, would be 1 squared, which is 1, and 1 squared, which is 1. So the area of the square out here would be 2. So the length of this side would be the square root of 2. Using the Pythagorean theorem, you can find that hypotenuse side length. Again, just going back to 1 squared plus 1 squared equals 2. A squared plus b squared equals c squared. And so we have to take the square root of it to get this side length. So that distance from here to here, from one corner to the other corner, diagonal across that single square, is the square root of 2. Now if I do that with this triangle, and again these are 45-degree corners and a 90-degree angle here, so a 45, 45, 90 triangle. If I look at this side length here, we can see that that side length is 2 units long and this side length is 2 units long. And if I were just simply to use the Pythagorean theorem and say this side squared plus this side squared, so 4 and 4 is 8, would be the area of the hypotenuse square. So the length of this side would be the square root of 8. But one of the things that we can go back to is the distance from one corner to the other across the diagonal of a square, or this hypotenuse length for this triangle, and see that that length, that distance, is from here to here. So that distance didn't change. It's still the square root of 2 from here to here. And then from this point to this point is another square root of 2. And so what that means is that the square root of 8 actually has to be the same as 2 square roots of 2. And we know that that's true if we take and we factor the square root of 8. You can factor square roots like you can factor other numbers. We're basically simplifying the radical and factoring it to the square root of 4 times the square root of 2, and we know that the square root of 4 is 2, and so there again is another way to prove or show that the square root of 8 is actually 2 square roots of 2 across. And if we do this one more time with another one, just making them a little bit larger so we can see this pattern that arises from a 45, 45, 90 triangle. So the right angle here that's 90 degrees. And our side length of 3, and another side length of 3. And again, just using the Pythagorean theorem, we could square each side and see that adding those two together, 99 is 18. So this side length here is the square root of 18 all the way across this distance. But again, going back to the original first one we did, is this distance is the square root of 2 from one diagonal corner to the next. And so you can see that we actually have 1, 2, 3 of those, 3 sets. So the square root of 2, the square root of 2, and the square root of 2. And what that means then is that the square root of 18 has to be equal to 3 square roots of 2, or 3 times the square root of 2. We'll just multiply 3 times. There's 3 of them, so it's 3 times the square root of 2 gives us that value. And we could have taken the square root of 18 and factored it to the square root of 9 times the square root of 2. 9 times 2 is 18. And there we again see that the square root of 9 gives us the 3. Square root of 9 is 3. And so 3 square roots of 2 is the simplified version of the square root of 18. And the reality is this is true for any or all 45, 45, 90 triangles. Really, literally, we can just simply look at the side length of 4 and 4 and recognize that if you look across the hypotenuse, there will be 1, 2, 3, 4 square roots of 2 across that distance. So we could literally just simply say, rather than going through the Pythagorean Theorem process, we can know that if we have the side lengths, we also have the hypotenuse length in terms of the number of square roots of 2 that it represents, in this case 4 square roots of 2. And so sometimes we like to generalize this idea. And in generalizing something, we usually want to take it and say something like, if I took any 45, 45, 90 triangle, so I'm going to just make a 45, 45, 90 triangle, at least close, hopefully. And if I just simply said, for any 45, 45, 90 triangle, if I know what the side length is, we'll call this x for this side length. And remember, this is really just half of a square. I really literally tried to, best I could, freehand a square and cut it in half. If this side length is x, then this side length also is x. They're the same. It's a square, so all the side lengths are the same. And then across this part of it, if I want to know how many square roots of 2 it is across, well, if we look back, this one was 4 square roots of 2 across, which is the same as the side length. This one was 3 square roots of 2 across, which is the same as the side lengths. And this is 2 square roots across, and even our first one is 1 square root across. And so our side length actually tells us how many square roots of 2 we need to get across the diagonal of any square. So the generalized version or form of this 45, 45, 90 triangle is, if these two are the same, this one is whatever x is times the square root of 2 to get the distance across the hypotenuse side of a 45, 45, 90 triangle. And so that's kind of a simple way of, if you ever run into a situation where you have a 45, 45, 90 triangle and you're given one side, one part of it. So all I need is one piece of the 45, 45, 90 triangle, and I can get the other sides of it fairly easily. And really all I need is one side, one piece of that. So I could even look at a, see these are 45, 45, 90 triangles. And because I basically took a square and cut it in half. And if I knew this side was 10, and that's all I knew. That's all I need to know. With a 45, 45, 90, because it's really half of a square, this is 10. And the diagonal distance across here is going to be 10 times the square root of 2, or 10 square roots of 2, because it's going to be 10 of those square roots of 2 to get all the way across. If I said this distance across was 27 for a leg of a 45, 45, 90 triangle, then the other leg has to be 27, and the hypotenuse has to be 27 times the square root of 2. If I were doing these on grid paper, you'd actually see the grid going 27 this way, 27 this way, and then 27 square root of 2 diagonal across this piece. And so that's why I started out on grid paper, so you could actually see that each of those distances is the square root of 2. And that's true. All we're doing is making this triangle larger or smaller, various sizes. We could even do them portions of squares. You don't actually have to go to the individual grids and still see that this always works. And so the idea here is, if we were to summarize, the legs of these are always the same length. They're always the same length. If I look at the legs of a 45, 45, 90 triangle, they're always equal to each other. 4, 4, 3, 3, 2, 2, 1, 1. The legs are always the same. The hypotenuse, which is the long side of a right triangle, it's across from the right angle. The hypotenuse is whatever the leg length is whatever the leg length is, like 4 or 3, depending upon the triangle, times the square root of 2. And so that's always true for any 45, 45, 90 triangle. And since it's always true, it's something we can always use. And we don't really need the Pythagorean theorem for these. I could have done 4 squared and 4 squared and gotten 16 plus 16 is 32. And I could have said, well, this is really the square root of 32, which would have been a little bit more work. But the square root of 32 could have been simplified to the square root of 16 times the square root of 2, which is still the same as 4 square root of 2, because the square root of 16 is 4. And that's how we use 45, 45, 90 triangles. And really useful because we only really need one side of the 3 to figure out the other 2 if we know it's a 45, 45, 90 triangle.